Welcome back, everyone. To continue on our discussion of machine learning theory topics, we're now going to discuss overfitting and underfitting, and how you can recognize if this is occurring in your own problems. So we understand now the full process for supervised learning: acquiring the data, cleaning the data, performing that sort of train test split or a train test validation split, and then training your model, comparing its results on the validation data, and then finally getting some performance metric on your test data, and then deploying your model to the real world. What I want to do now is touch upon the important topics of overfitting and underfitting. So overfitting is when the model fits too much to the noise from the data, and this often results in low error on training sets, but high error on your test and validation sets. So let's actually take a look at what overfitting would look like for the example case of a really simple data set where you just have one feature X and you're trying to predict Y. So here we have a bunch of training points. And so there's some single feature X, and at the end of the day, we want to build out a model that can predict Y. So a good model would try to fit the general trend of the actual data set here. So we can see it appears that there's some sort of positive slope, and it looks like it levels off later on. So what would happen if the model overfit to this training data? So when you actually overfit, what's going to happen is you're actually going to fit too much to the noise of the data. So here we have what appears to be a really bad model. But keep in mind that this model is technically hitting every single one of those training points. So your error here is actually going to be extremely low. And in this specific example, your error is actually 0 because your model is accounting for every point in the training set. So your error just on the training set is actually really low when you're overfitting. So that's why it can be really deceptive. And that's why we also need the validation and test sets in order to understand whether or not we're overfitting, because just the training data alone won't tell us that information. So what happens when you're overfitting is you're fitting too much to the noise of the data here. And so if you were to get a new point, and this would be a test or validation point, if you're overfitting, that means you're getting low error on the training set, but when you get a new test set that the model hasn't seen before, you're going to get a much larger error off your model. Now let's think about underfitting. Underfitting is when a model does not capture the underlying trend of the data and does not fit the data well enough, kind of the opposite of overfitting. And this results in low variance but high bias. And underfitting is often the result of an excessively simple model. So in that same situation, if we were to have the features X and the label Y, something that was underfitting would just not even be able to grab the general trend. So maybe it picks up on that first upward slope, but doesn't really grasp the idea that this model should eventually level off for that value of increasing X. Now this particular data set was really easy to visualize. We just had one feature X and one label Y. But how can we actually see underfitting and overfitting occur when dealing with multidimensional data sets? Well, let's first imagine we trained the model and then measured its error over training time. So let's begin with a thought experiment. Let's imagine we have what should be a good model. Well, as you can imagine, a good model, when it first encounters the training data, it's going to have kind of a large error because it hasn't actually seen this data before and it hasn't adjusted any internal parameters to this data. However, as you train your model for more time on the training data, you would expect that error to essentially go down until it levels off and converges to some sort of minimum error. So this is what a good model should look like. And when we're specifically talking about neural networks, this training time actually has a specific word, and depending if you pronounce it the American way, which is epic, or the British way, epoch, which is the way I pronounce it, essentially one epoch is passing the entirety of your training data one time through your model. So we can see here as we do multiple passes on the entire set of the training data, eventually our error will converge to some sort of minimum. Now this is a good model. But what would a bad model do? A bad model, if you train it for more and more time, would get increasing error. And that's not good because essentially your model's not learning every time it goes through the training data. It's actually increasing the error. So we have the expected behavior of a good model and the expected behavior of a bad model. So how can we use this intuition then to understand what overfitting or underfitting would look like during the training of a model. So in thinking about overfitting and underfitting, we want to keep in mind the important relationship of model performance on the training set versus that test or validation set. So let's imagine we've split up our data into a training set and a test set, and we're going to color them here. So first, we would see the performance on the training set. And typically, your training set performance is going to decrease in error as you train it for more epochs. Next, we check the performance on the test set. And in an ideal situation, you'll get similar behavior. The test set, as you train for more epochs on the training data, then your error on the test set will also decrease. So it should look the same. That's the ideal situation. So ideally, the model will perform well on both with similar behavior. But what would happen if we were to overfit on the training data? So recall from that simple example of just that single feature X and that label Y, if we were overfitting on that data, we actually still get really good performance on our training data. However, once we introduce that new test point or that new validation point, that's where we start to see a large error occur. So that means we would start to perform poorly on new test data if we were actually overfitting. So often you'll see something like this occur, where we have that red line as our training set, and then that blue line as our test or validation set. And essentially, this indicates that we're overfitting. So this is a good indication of training too much on that training data set, and you begin to overfit. You've done too many passes on that training set, and now your model can't generalize to data it hasn't seen before. It's only been able to predict now really well only on data it's seen. So what we want to do is we want to make sure we don't train too much on that specific training set so we can still generalize to new test or validation data. And what we can do is we can plot out this behavior on the training set versus the test set. And then you should look to have a cutoff point on that training time. So as you can see the error on the test set start to increase, that's a good indication that that's where overfitting on the training data would begin. So you want to kind of choose that cutoff point. And it's not always as clear as this where essentially they intersect, but the main idea being if you see an increase in error on that test set as the training error is still going down, that's a good indication that you should stop training there. And this is an idea we'll touch upon later on in the course. So as I mentioned, we'll check on this idea again when we're actually beginning creating models. For now, let's just go ahead and be aware of this possible issue and keep it in the back of our minds when we're actually creating and training our models. Okay, thanks, and I'll see you at the next lecture.